Hi everyone, it's Mr. Lim here again, and this is our final video on carboxylic acids and their physical properties. Okay, so physical properties of carboxylic acids. Again, we're doing melting boiling point, solubility, and vapor pressure. Okay, these are all things we're always going to talk about in terms of physical properties. Okay, let's get started. So, carboxylic acid groups add hydrogen bonding to the molecule. The hydrogen bonding between carboxylic acids can be shown in this diagram that I'm about to draw. Okay, that's one methanoic acid. All right. And then here is another methanoic acid. I'm going to draw it in a very specific way. I'm going to draw it in a different color as well because that will make it easier to see. All right. Okay. So that there is drawn that way so that we can draw the hydrogen bonding that goes there and the hydrogen bonding that goes there. Okay. So we draw them one up, one down just to help that to be drawn a bit easier. Okay. So when you have the double hydrogen bond there, those hydrogen bonds are very strong and they hold the two molecules together and they form a structure called a dimer. Okay, so that's when the two carboxylic acids double hydrogen bond together to form one larger molecule. So then let's draw it again for an ethanoic acid one. So 1, 2, 3, 4. Oops. Okay, here's your dimer structure for two ethanoic acids. OH, bond O there, and then you get some there, with the hydrogen bonding there and the hydrogen bonding there. Okay, so this whole structure then is a dimer. Okay, that's a dimer structure. What's the point of this? These things stick together through the entire substance as dimers. Okay, and when you have dimers, what it does, it significantly increases the size of the molecule. Because instead of it being the molar mass of what it is, it's actually double now its molar mass. Double rainbow. No, double molar mass. Okay? It has double the molar mass. And because it has double the molar mass, it now has double the size of the dispersion forces. And if you remember, as you go up in size, you will have greater dispersion forces, and at some point, the dispersion forces are going to take over as the predominant force holding stuff together. So now, when we have carboxylic acids, the increase in size means the increase in dispersion forces holding them together, which means they're going to have a greater sum of intermolecular forces, or van der Waals forces. Always remember, we're talking about the sum of forces. Okay? So, that means compared to similar organic molecules of similar molar masses, carboxylic acids have a significantly larger sum of intermolecular forces because of their significantly greater dispersion forces. Okay, so it's effectively doubling the size. So if you're comparing, so let's go through that. So carboxylic acids have a high melting boiling point due to their formation of their dimer structure. Okay, so they have a much greater sum of intermolecular forces. Right, dispersion forces are much larger than comparable sized molecules. Okay, because effectively you're doubling the size of the thing. Carboxylic acids do form hydrogen bonds with each other, but the increased dispersion forces has a much larger effect on the boiling point of dimers. Well, carboxylic acids. So let's have a look here. All right, this is the acids, alcohols, aldehydes, and alkanes, and you can see that acids have the highest boiling points. But the whole concept is there. What you're doing is, if you compare this one here, the carbon with number 2, you really are thinking about it's double the size of the thing. So it's like it's actually a number 4, if that makes sense. All right. And so if you see that the 4 alcohol is there, so it's acting as if it's double the size. All right, acting as if it's double the size. Okay, and you can see that that pattern is kind of held throughout, but not really. But the idea is that it's just going to have a much larger dispersion force. Okay, so that's the idea there. As you get bigger, you're going to have more dispersion forces, greater sum of intermolecular forces, more energy required. Don't forget to talk about the energy required to break the bonds between them, to boil them, or to whatever. All right. The presence of hydrogen bonding in the molecule means that carboxylic acids are soluble in water. Okay, so what happens is that okay, we know about solubility. The hydrogen bond between water and carboxylic acids means the small carboxylic acids are completely soluble in water. The larger end the carboxylic acid, the greater the effect has the hydrocarbon end. So we've discussed this before. The greater that side part there is compared to this part here, makes it has less solubility. Okay, blah blah blah. Okay, this is the part I wanted to get to. Okay, when dissolved in a solution, the dimer structure will separate. So here you have two methanoic acids in a dimer structure. Okay, in a dimer structure. What happens is that when that's dissolved in water, this can now hydrogen bond with a water molecule. Okay, maybe it'll go like that, and it will form hydrogen bonding here and here. Okay, and the other methanoic acid that was bonded as a dimer to that one there can also bond with the water molecules around it. Okay, where's my yellow? Here it is. Okay, and then this size here is actually really small, so it's completely soluble in water. But as you get longer, that dispersion forces over there start to take precedence over that hydrogen bonding there. Okay, so that's the concept that solubility, when they break up the dimer structure and then they hydrogen bond with the water there. Right? Yeah, see, ethanoic acid and water. You draw that yourself. Okay, so you can see that the solubility rapidly decreases after 4. All right, and then once you get to 8, it starts to become totally insoluble, because the size of that carbon chain, 1, 2, 3, 4, 5, 6, 7, 8. Okay, this part here is super soluble, this part here is insoluble. Okay, so, and this structure here that I've just drawn, we're going to get to know this structure lots when we do soaps. Okay, the whole idea of a polar head and a non-polar tail. Okay, let's move on. Vapor pressure. Okay, moderate vapor pressure, because they have that greater dimer structure. All right. Again, we've all dealt with this before in other videos. You can have a read of it and you can take down the notes if you want, or totally skip these notes considering you've written them like how many times. All right. And so here is a couple of diagrams. Vapor pressure. Remember, the stronger the sum, the greater the sum of intermolecular forces, the greater that sum is. What will happen to the vapor pressure? Do you expect it to go higher or lower? You expect it to go lower. The lower the vapor pressure. Okay, because the vapor pressure is a sign of, high vapor pressure is a sign of weak intermolecular forces. Okay, so you see here the acetic acid is all the way down at the bottom. Okay, what's above it? Propionic acid. That's not a mistake, that's a different thing. So propionic acid. Water is down there as well, but you've got your methanols and stuff like that. So your methanol and your acetic, your methyl acetate and stuff with a reasonably high vapor pressure there. All right. Okay, because it has, even though it's got hydrogen bonding, it's not going to have those dimer structures to give it the strength that you've got in other things. Okay. Also, methanol is only a single size, when acetic acid is really, with the dimer structure, it's got 4 carbons, so it's quite large in comparison. All right, that's it. And then we're going to get on to identifying the different things. Adios.